Hi, Suviksha. So yesterday I changed the meeting settings. Can you help me know if you can still raise your hand and are you able to unmute yourself? Um, okay, we'll just wait for a few minutes for everyone to join and then we'll start from 6:10. Okay? Yeah, so today we have changed the settings a little bit, and everyone is required to verify their mail IDs before joining. So we'll wait till 16 for everyone to join, and then because of this procedure, and then later from 16 we can start the session. So, hello. I guess most of you have joined. So, we'll begin the today's session for week 2. Let me just share my screen. Uh, yeah, yes, Sarvesh. So, uh, wait. So from today on, we'll follow a system like, as you might all have noticed that while logging in, you need to verify your mail ID just because of the incidents that happened yesterday. So you'll be given permission after you raise your hand. I'll allow you to enable your mic to be on and off, and then accordingly you can say something or if you need to ask something. That way, it will ensure that our session is going smoothly, and if you have any doubts or something, that will also be answered accordingly. So, for now, I have disabled camera for everyone because in the last session something happened that some people directly turned on their camera and then something that not had to be seen would was seen. So these videos are then posted on YouTube and then we need to follow certain policy over there. So then I had to crop the video accordingly, bits of sections of it. So now for now I've allowed because I saw okay today everyone joined with their cameras off and then you're allowed to turn on your cameras. So that was something that, okay, will follow from now on. And probably if that muting, unmuting thing and kicking meeting does not happen today, then this link would be finalized for all the coming in sessions. I guess it's 6:15 already and we have a couple of students here. So we can continue with today's session. So where we yesterday ended was we were seeing some statistics how so this is like content for week 2, but where we yesterday were that we saw the different types of data types. We went on from why to do data analytics, learning objectives of it, how different types of data are arranged, how data helps us to add some value into the business, how analysis is different from analytics. So in a way we saw that okay how both of them are also linked and how people with different roles contribute to the field. So now, then we also looked into some programmings that's like Python and wait, I guess couple of them are also joining now. Just together more. Okay. Then we went and saw some couple code bits that okay how to do extract particular rows and columns. We saw certain fundamentals, how to subset a row and column, how to take out unique values out of them, how to group them accordingly. And then we went to a part of seeing that if it's pandas library or python library, how common description it gives to them. And then there were nothing but different types of plot and measures of central tendency. Followed by measures of central tendency, we went into a bit where so okay, this is for today's content. So then we went that okay, what are the different measures of data locations? We saw arithmetic mean, weighted mean. So for the formula basis, you can refer to the slides. Sir has also solved. Professor Ramesh has also solved couple of examples over there. How the different formulas differ for group data and how they are for if you have a population specific data or sample data. Then we saw the measures of dispersion, the like skewness, kurtosis. It's like we just discussed about them. We didn't actually we I also didn't have any content on slide for the same because it's exactly replica of it. So why waste double time over there to look into the videos also and to look over here also. Wait. So after following the same, we saw that okay, how mean, median, and mode differed for a particular data. So we'll just have a quick round that one who knows the answer can raise your hands and I'll, or perhaps now also I can allow everyone to give an access to the mic probably because I hope that's fine. Okay. So you can unmute yourself and then so you all have access. Oh, please don't start it. Okay, so we'll follow that. If you want to say something, then only you unmute yourself and then say something, because that will help us go smoothly. Okay, so we saw that what skewness was, how we see that a data is being distributed. So then here, can someone tell me what a positively skewed and negatively skewed data is like? So I guess you
Yes,
have.
ma'am. If excuse me, ma'am. If data
Yes, yes.
symmetric, then it is I think middle value. Or if left, then negative, and if right symmetric, then it is I think positive.
Yes.
Yeah, I
So
think that.
yeah, yes, so that is correct, but I'll suggest the way of saying or the wordings should be corrected in that sense that your data is not symmetric here, the data is skewed. So you should say something like, okay, the data is negatively skewed if it's left tail, the data is positively skewed if it's right tail data, because what we define to the term of symmetry is that something as normal distribution or Gaussian distribution. Okay, so then if you have a normal data set, so normal distributed data, is the mean, median, and mode equal or not?
Repeat, ma'am. Please.
Yes. So if your data set is following a normal distribution, or if you have a symmetrical, nice bell-shaped curve, so do you have all mean, median, and mode equal or not?
Yes, ma'am. In this case, mean median mode will be equal.
Equal. Okay. Now, if it's negatively skewed, you know where the mean will lie, that okay, where the data tendency follows. Median would be in center of it, and mode is like the maximum occurring frequency or the maximum value of the data set. So how the order would be if the data set is negatively skewed, which would be greater than or lesser than something.
The majority of the data points are concentrated to the right side of the distribution. So
Left.
the tail on the left
Hmm.
side, right?
Left side. Yes.
Uh, so that means indicating that values outlay like in the left side, less
Yes.
value.
Oh, yeah, yes. So, how are your mean, median, and mode then? It's like which is greater than which,
The mean is typically less than the median.
and then mode?
Mode will be in the center. I don't
Maximum.
know.
So mode
Maybe
is the maximum value of your data set or the frequently occurring values. So your median is always the 50% value. So you'll have the mean very less than the median, and then that is very lesser than the mode. So mode would be the maximum value of your data set. Similar thing will follow for if it's a rightly skewed data set. So we'll have the mean greater than median greater than mode, because now the data set is whole rightly skewed, but mean is actually the value where you see that where the average of the data set lies. Okay. So then we have something that relates to the bell-shaped curve, that how you define the standard deviation mean around to your observation. So we'll see that when we plot it. I checked out the lecture content from week 2. The lecture content is mostly very theoretical, and we have a couple of numericals there also. Yes, Gaurav and Kusum.
Hello, ma'am. Hello, ma'am. I have one question. That what is
Yes.
skewness? Can you, ma'am, please explain this positively skewed and negatively skewed one more?
Yes, sure. So skewness is nothing but a measure of dispersion. So you see how skewed your data set is. Now, if it had to be negatively skewed, we say that the data set has a very heavy left tail. So it's something like which is tail towards left side and it is leaning to, but that is not actually possible. But if your data set is like say positively skewed, or we say the right tail data set. So you have your peak towards something say 0, and your data set would be heavily tailed towards the right side of your data. Say probably you have your data points in between 0 to 10. Okay, I could have plotted it. Probably I can plot and show you how it differs. Wait, I'll share my screen. Mm. Okay, is my other screen visible?
Yes, ma'am.
I can't actually hear someone is talking, but the voice is cracking. So you say your data set is positively skewed, or okay, say let's just start from the basics that these are the axes that you define, okay? And
Ma'am,
you
also
say that
explain
your
what is skewness actually. Ma'am, what is skewness actually?
I'll say. So you know the normal data set or the normal distribution will look like something. That's it's like your normal data set. Okay. Now next, if you have something as okay. Next, if you have something like this. So here what you see, this point to this point is nothing but how dispersed your data set is around the range of values that you have. So this is like what tells you the dispersion from this to this point. Now to measure it, people for certain data sets which are like say like this, or certain data sets which are say like this, people say that your data is skewed. That means that it has certain majority of the values are only concentrated to one range and another majority of the values are only concentrated to one range. They are not symmetrically distributed how it's like in case of normal distribution. So this kind of data set which is like this, which is heavily tailed right side, you call it as positively skewed data set, or it is right tail data set. Now data set something like this which is nothing but heavily tailed towards your left side, you call it as negatively skewed. Why negatively? Because something like this is not possible. Now this is like you consider it when your data set is following across this zero axis. Now if you have something like this thing never exists because probability always exists in between 0 to 1. So we say our all the data set being negative is even not a realistic state. So negatively skewed is something a very idealistic situation, and just to name a negative or almost similar position, people just say it as negatively skewed. And something like this is called as rightly skewed or positively skewed data set. Is it clear?
Yes, ma'am, it is clear.
Okay. Yeah, okay, so this is done. Okay, we'll be back to where we were. And 2 minutes. My screen is visible to you guys or not?
Not visible.
No, ma'am, it
Yeah,
is not visible. Now it is visible.
yeah, bugs.
Yes, ma'am.
Now it is okay.
Okay. Okay, let's start from here. So, yeah, someone wants to say something? Hand is raised. If not, we'll go on. So those were like the measures of dispersion or measures of dispersion, how we said that okay, how different values are, and how do we say that our data set is. So these were like this, and these are so now if you have a data set where your mean median mode are not equal, so they are definitely skewed, and in that case you use skewness or coefficient of variation, the measures of dispersion, to define your data, to describe your data set. That is why this kind of things are being made. Now, how to compute them and the formulas for the same are there in the lecture content, and hence I have not shared over here. So we'll just go with how it follows, and next later we also have that how along with the normal distribution we define the data set across different characteristics. Okay. So yesterday we were here. We saw how the different measures of central tendency were. We saw the mean, median, mode. Then later we tried computing a percentile. We saw that okay, median and that particular percentile is same. We tried making a loop. So we saw that okay, if we define a particular list and then we want to print certain values. Okay, I'll have the pop-up here. Okay. Someone wants to say something? Hands are raised, so if you want to say, you can unmute yourself. If not, we'll go. Okay, so then we looked at for loop, that how if you have a list and we want to, it's like we just define some values and we directly print it. So everything will come on its own. But what if I want everything to come one after one another? So what we do is like we make loops. So what it will follow that, okay, I give them some increments, and based on those increments, those values would come up. So something like here is like I gave that a list and then I'm printing k, so it will tell me, okay, first 1 is there, 2 is there, 3 is there. Now if here I give it something like, okay, I have to print it in terms of indices. So that way it will print. So for I in this particular case, it will print the I value. So how many values it has. So it will first print I, then 1, 2, and then whatever variables you have next. Okay. Next, similar to the range. So that is why we saw this range function. That this like it didn't had much of the meaning when we were learning the measures of central tendency or dispersion tendencies, but it's like helpful if you define some functions or you make some loops. So in that way, range helps you to easily access your data or index your data set. Now, suppose in cases you are directly trying to access certain folders, and those folders are like you don't know the names of the folders, or neither you want to write the names of the folders. So what you do is like you give it, okay, for 1 to n. So all of the folders that are there in the directory, access them. How to access them is like increment by 1. So similarly, so you use range kind of functions in those phases, or else you can also use shape, which will tell you what's the shape of that data set, and you just go from 1 to the last value and you increment it by 1. So for here is like how for loop follows. So for I in that particular range, following, so here 2 is the last the incremental value, and 10 is the first value, 20 is the last value, and it will increment in terms of 2. So here normally we are just trying to print it. Okay. Similarly, now if you want everything to come in a single line, and that to be followed by a comma, so you do something like the end, which is followed by a comma, give it some space, and then print the next value. Okay. So then there are certain functions in Python. So if you want to, what we also read yesterday, that mean, median, mode were indeed the functions in Python, and that is why you should avoid using the name of the function as variables. So that whenever you define a function and you want to use the function next, how you define it is like followed by parenthesis next to it. So you define a function. So see, is like define. It's just another English word. So you use it indirectly here, define. Whereas in MATLAB or in other languages, you need to write
ma'am,
like
you are not
function.
audible.
I'm not audible?
Ma'am, you are
No,
audible.
Maybe
We
you
can
are
hear you,
audible.
ma'am.
no,
We
man.
can hear
I
you.
think your voice is clear, man.
Yeah, okay. Thank you. Probably you can try turning on your audio or something.
I think
Okay.
network issues there.
Okay. So then how we do so is like you just print it. So this is how I have defined a particular function. Oh, I guess all the values are printed here already from start. So you define a particular function and then you print that function. It's like how to access this function is that you give it those parentheses and then it will help you print what it is having in it, or it will proceed the next set of command lines that are in it. Similarly, we define a function called as add. So what this add will do is it will give you those certain two values. Okay, if you're defining a function of add, given that I take two inputs of P and Q, now here you can also say that, okay, C is my next output, but it's fine. If you are directly having the output in return, why instead give one more comment to it? So then I say that C is equals to P plus Q and print that value of C. So if I define the function of add of 5 plus 2, it will give me something like this. So this is the way how you define simple functions. Yes.
Excuse me, ma'am. I have questions when we define the address like functions. So it is a system. It is a user function, or it is automatically inbuilt like function add. We can
Yeah.
create in add.
So here
Yes.
what I'm defining is my inbuilt function. Add is not a function that is existing. It's like you directly have this plus symbol over here because that actually comes within the NumPy libraries. But if you define something like mean or this min max, you need to ensure that what you are having as variables, those names are not matching to your actual inbuilt libraries or functions, which is like, okay, now you know mean is something that everything might have. Average is something that might also be, so avoid accessing those variables. Here, it's a generally defined function. So it's a user defined function that I have here. So I have normally as add and I'll define it. So it's fine like that. Okay, so similarly, if you want to find the minimum and maximum value of a function, you just do min of data and maximum of data. So here min and max are the functions that are defined by the system. So those are inbuilt functions. Whereas if I want to have my own function that will define min max of the data, so I give something like min underscore max. So it will give me min of data, max of data, and then return those values. So towards the end, I can just access the variable in this particular function as min max of, give the parenthesis, pass the data along with it, it will give you the value. So this data was it. So I directly passed it and I got the data values. Okay. Similarly, if range, now range is also an inbuilt function, but now we defined it in a way that it will give us the differences in between values. So we are not using the inbuilt function. Instead, we are using it to define our own function. So it gave us something like this. So range also gave. Now another question was, what was quartile? So if yesterday did we see, okay, we didn't. Okay, so let's just first try and plot or is like visualize our data in the form of box plot. So if you might have seen the data that we have, sorry, Rohit Kumar, please mute yourself. Okay, so the data that we have is something like this. We have different subjects for each of the persons and their genders following next to it. Okay, so what we want to do now is we want to plot its that particular person's only maths. So we want to plot the it's like marks that the person might have got or all the population has in maths. So how we do that is like we'll just get this
Hello, ma'am.
particular library. Hi, yes.
Ma'am, can you please zoom the screen?
Zoom the screen.
Yes, ma'am.
Okay. So sorry. This much works.
Then please zoom more because it will be easier for us to see.
Okay, I guess in my other screen. Are you accessing using mobile?
Yes, ma'am. Now I am accessing in mobile as I am in my college.
So I guess probably for other people who are using laptop, their aspect ratio might change. Wait, I'll just see if I can do it for
Oh, we
both.
can zoom using mobile too.
Hi, so if you can zoom, then you zoom, right?
Okay, ma'am. Okay, ma'am.
Okay. Because the aspect ratio will then change over here also. And then for others who are using laptop, it would be too much zoom. Okay, anyways. So if you plot a particular file in a way, so if you want to see how many number of variables or values are there in this particular field called as maths, you import this library, pyplot from matplotlib. I just define a variable as plt and plot this particular box plot over here. I'm just giving the data set in it, that is was my x, and sm here stands for a symbol that I want for my outliers or particular variables that are there. I can define that particular symbol as any symbol that I want. Okay, and then I show it. So plt.show will give you the final output. If you don't do plt.show, it will show you how the plotting is being done, and there will be certain number of written text followed by it, and there your plot would be there. So okay, here you see a box plot. And the line that you see over here, the orange line, that is nothing but it defines the median of the data, where your median is. Now this line is not in the center. That means that your data is skewed in a way that it's not normally distributed. It might have some extreme values. It can either be positively skewed or negatively skewed. Okay. Now following it, we want to see, so in a particular box plot, how data follows is that you have three different quartiles. What those quartiles mean is data that is 25th percentile, that is 25% of the values might be below it, but 75% values are above it. Okay, so how a box plot is usually defined as, it will start from below. So this is Q1, this is Q2, and above is Q3. Next are the outliers above it. Okay. So we say that 25% values might be below it, whereas 75% values are above it. So that is nothing but something 100 minus 25, you have 75. Q2 is the quartile that represents your median of the data. So that is nothing but 50th percentile. Percentile stands as X% most of the data is less than it, and another 100 minus X% is at least above it. Okay. And then last Q3 is the above one. So that is nothing but 75th percentage of the data or 75th percentile. So that particular data is below it since we had 25th percentile. And then only 25th percentile is above it. Percentage is above it. So be careful in your terminologies how you use percentile and percentage, because percentile is something which will tell you that how much values are just the number of percent. It's like 100 minus those X% is above a certain value. So to compute percentile, you need to have an index of a particular position. You take percentage and then you multiply with the index of position. So it's not as same as that of percentage where you directly take sum of them and then divide it by 100. So percentile actually tells you is like, say I got 90 percentile in my class 10th or class 12th board. So I'll say that 90% of students are below me and 10% students might be above me. And that is where I belong to. That is why in some cases we say that, okay, I don't want percentages, but percentile looks nice because I got a good values of percentile, whereas percentage is an absolute term and percentile is a relative term. Okay. And then if you want to see a difference in between them, so the most extreme two quartiles, first is the lowest more quartile, that is nothing but Q1, and another is the higher one, that is nothing but Q3, so the 75th percentile. You get a difference in between them that represents your interquartile range. So this interquartile range is nothing but difference of Q1 minus Q2. So this is the metrics that you have if you follow a if you have plot your data as box plot. Now this matrix you will, so there are certain ways. It's like how you plot your data is like, you might not, it's not necessary that, okay, box plot looks nice to me, so I'll always plot it, or bar graph or bar graphs, I like those bar charts and I'll always plot those. It's like if your data follows a certain distribution, then and then only you should plot these distributions. So there is a saying, people say that box plots you can plot for everything, if either your data is normally distributed or not, but bar charts you can't. For bar charts, you can also plot it for everything, but it does not give you a statistical sense that how and why you are plotting. Box plot, if here, as you saw, we see that my median is lying below it. So I can say that my data is not normally distributed, it's skewed to an extent. So here it's directly interpreted, but for bar charts, it won't be. So try to plot your data in a way that it represents the nature of the data and how it is statistically representing your value. So it will also add some actual significance how you are even reporting the data set. Okay. Next, if you want to plot the variance of the data set, it's directly inbuilt function followed by variance. Similarly, we had plotting now the population stats. So yesterday we had mu as a population parameter. So here what we're looking at it is nothing but the entire population. But in our case, since we have a local data set, our population equals to our sample that we are looking with. So it can become termed as a population parameter as well as a sample parameter. Okay. So then I plotted the stats variance. So there's a library in Python is like from statistics, that is stats. How you hover over here and you looked what are the parameters, how you define a particular statistical library, how it is being written, how there are different formulas, STD, WE. Then you also have population variance, so you have P variance. So if you want to learn about a specific library, just define it, hover over here, and then it's like over the particular function name, you will be able to see that what that particular library has and how to define those functions also if you are not known to it, or while Googling, you're not able to understand how you exactly want to do. Okay. So then similarly, we do, this was normal variance that I did. So probably it might be some sample variance, population variance, I don't know. Next, oh wait, some people are joining. Okay. So what we did is I directly plotted this variance, then we did this population deviation, and then we did variance is nothing but square of the standard deviation. So you see we got a difference in between the variance computed there and variance computed here. This is because we don't know what that particular variance might be. It might not be population variance. Now if you want to see population variance, let's try doing this p variance that we just looked now. Okay. So let's see if the values are same. So yes, the values are same. So what we initially computed was something else. Now why sample statistics differ from population statistics is because sample statistics involve the concept of degree of freedom. Now degree of freedom is something where you need to assess that each and every value is very sensitive to your data set. Now it will look at, okay, if I remove the lastmost value, what will happen to my data set? If I don't remove, what will happen? Whereas population statistics are something that will look at the holistic view. Will look, okay, how the data set is varying and how your values would be accordingly. Someone wants to say something? Okay. So similarly, as we just saw that what skewness was, so we'll just plot that, okay, we'll see if my data is skewed or not. So now it gave me 0.8. So yes, my data is skewed that we saw in this particular box plot. And then it also gave me a corresponding value. Now for the distributions which are skewed, we saw yesterday were the central tendencies, and we also saw now, can someone name those, a few of them? That if my data is skewed or my data is not normally distributed, what particular statistics or particular measures of tendency, central tendencies can I follow to describe the characteristic of my data set? Someone? Anyone? Well, we saw skewness, so you'll see how your data is skewed. Then there is another parameter called as kurtosis. You see the peakedness of the data, how much population is there in the peak and relative to the tail of the data. Now we saw this interquartile value, so the range of the functions, how your data set is distributed. Yes? Probably a fluke. Okay, then we saw variance now. Then there is standard deviation. There is also a standard score and coefficient of variation. So these are just different parameters how you define. Now, yesterday we saw that, okay, we'll plot something and we'll make a box plot of something. So let's do it like, okay, you define a particular function. So this df here is a data frame which has all of our data set. We'll just plot it. So this is just a random plot. So this is when someone would do where he or she does not know about the data set and they just want to visualize probably that, okay, how the data set looks like. Because looking the values in a table will make you feel more bored than directly visualizing them. So you see them, see how the values are, how the data set is. Now from here, you can say that, okay, history has a data set which is somehow normally distributed, but you can't exactly say that unless and until you do some statistical test to see if it's normally distributed data set or not. Okay. So this is how you plot that. Now, suppose our data set was something that you had n number of people. Within that also, we had two different, so we have people by different genders, so male and female. And we had two subjects, let's say maths and English. So I define those. I want to plot a scatter plot of them. Okay. So I want to see how the for maths and English, and then I'm grouping them by the particular people. It's like if it's for male or if it's for female. So then what we do is like first we group by gender, then if it's a particular gender, and then we subset them using maths and English. And then if you want to give some colors, differentiate them by colors. If you want to differentiate by a marker, you differentiate them by a marker. So here I've also given the marker basis. Also, yes, Anand.
Ma'am, can you explain your block box? Because I can't understand which line to represent what is this. So can you, ma'am, please explain this graph?
Sure. So
Yes,
in
ma'am.
this, oh, huh,
This graph, this diagram.
yeah, yes. So if you see this particular graph, you see here there's a
This graphic look like a candle, trading candle. You know that?
Candle. Okay. So here what you see, the orange line, this orange line represents the median of the data, where your median is following. And then here, the last most point represents your last extreme outlier. The here, it represents your maximum outlier. What you have, these bars over here are called as the quartiles of your data set. So while representing a box plot, you don't just say that, okay, I have a, okay, someone unmuted them. Okay, so while representing a box plot, you can't just say that, okay, value was lying above the some upper T or upper value. And so there are certain criterias for it, how you define a box plot. So there are different quartiles for the same. So the upper one is like, sorry, the upper one is represented by the Q3, that is termed as the 75th percentile or the Q3 quartile. Then the lowermost is the Q1, and the orange line that I just showed represents the median of the data, and we just saw that median is nothing but 50% of the data. So from which you can also say how your data is being distributed. So that is the Q2 quartile. So that is how a box plot is being normally distributed. It's like being shown that you have 3 different quartiles and you represent your outliers which are above those quartiles. These quartiles follow the distribution of 25 and 75%, and in between them, the range is like differentiated by 50. So that is how a particular data set is. Box plot will also, box plot is, and box plot will give you an understanding of how your data is skewed. Also, it will tell you if your data is normally distributed or not. Well, of course, to see if the data set is normally distributed or not, you'll do statistical test as t-test, you'll do ANOVA, all those things you'll do. For normally distributed, you'll do Anderson-Darling, you'll do Shapiro-Wilk, you'll do this particular test to see if your data is normally distributed or not. But using a box plot will make you easier before the data set. That's like, you'll do this test eventually, but to see them, that okay, if it is or not, or how my data set is, because you won't actually direct always plot your data values. So here you see that median is on the lower extrema, or over here you see that the median values are not exactly in the middle of the plot. So that is how I can say that my data is not normally distributed and my data is following some skewness because the median is lying somewhere else. Because if it was normally distributed, both of these 3 values would have been coincided like that. So was that clear?
Yes, ma'am.
Okay. Someone has his hand raised. Any question? Hi, yes, go ahead, Govindu. Oh, on hold. Okay. So then we were on scatter plot, that I want to group my data with 2 specific subjects, and then I also want to see how males and females have answered or have their questions. You want to say something, Govindu? Okay. So then we plot a scatter plot. So scatter plot is something, it looks like this, where you have your data set. It's like there are 2 independent variables. Usually x-axis is dependent variable where y-axis is dependent on x-axis. But here there are 2 independent variables which are grouped by the values that we give them. So it is grouped by the gender over here. So we see that how females have scored in maths and English, how males have scored in maths and English, and how their particular characteristics are. So usually, what people do is like using the scatter plots, they also see that how different your data set is. Suppose I have 2 different groups, say group A and group B. So people will say that, okay, how this group A and B are also differentiated from each other, or how they are different from each other. So what is like using now current techniques of ML and AI, they do some plane based methods, or what previously or now also some people do that. I also do that. What we do is we take the cluster of the data, we see where the center of the data is lying, and then we compare it with all the different values. And then accordingly, we find the score. That score is something called a Silhouette score. And we say that, okay, we are able to make a good discrimination if the value of the score is, say, so for that particular score, the values are within 0 to 1. We say if it's a good cluster, so it's greater than 0.5, a good cluster to separate my two data sets, say A and B. And if it's not, then the value would be less than 0.5. Further, to even differentiate it, there are different statistics to say that, okay, how different your data set it or clustered it, or if you increase the sample sizes, like you not only take A and B with n number of samples, but if you take A and B with like hundreds of samples, then will you be able to differentiate them or not? So there are like it's like scores such as Cohen's d or something to differentiate your data set. So that is how you'll be able to see in your data. So now we just saw that, okay, how the skewed distribution is. So it's like something like this. So it's like I just plotted a random data set, gave it some value. So exponentially it will decay and have n number of samples. And I plotted a histogram of it. So plt.hist will give you a histogram of your data set. You can again hover over the hist function. You can see how many properties that particular hist function has, its own library. And we'll see that, okay, what we can do, can we label it, can we stack the values, can we align that particular it. So we have different functions for the same. Here you see it also provides you an access to define tuples, to define list, arrays, polygons, and all others. Okay, and then there is another parameter called as bins. So bins is how you someone's waiting in the library. Okay, so bins is how you distribute your data within specific bins, where each and every bin will show you the number of variables or the frequency of variables that are there within one. So yes, Anisha. Probably nothing. Okay. So that is how a histogram is defined as. Okay. Then if I want to plot I want to plot a normal bell-shaped curve. Okay. So bell-shaped curve is nothing but my normal distribution data. So normally distributed data. So here you just saw that what I did is I commented all the data set. How do you comment a data set? You just press control and question mark. So you will be able to comment it. Now, if there's something called as a loop and I'm defining a for function above it, and I want to say align all of my data set. So what I do is like, I'll do tab there. So you see those arrows over there, and then you see that, okay, if this red thing comes up, so you see that, okay, there's an issue with the alignment. So you want to go back to the previous thing. So what you do is like, you'll do shift and tap. So it will bring you back to things. So these are some shortcuts that will help you proficiently program, because using shortcuts, like not just always that, okay, you'll do space, you'll do delete. That just does not follow when you are doing lump sums of code. So this kind of shortcuts will essentially help you to efficiently code your program. Okay. So where we wanted to see how a normally distributed or a beautiful bell-shaped curve looks like. So similarly, we did something like this, defined a data set and then plotted a histogram of it. Now here I'm just plotting n number of random values and said that particular random values follow a normal distribution. Okay. So here my random values are following a normal distribution and how they look like. Now, if I say I want to know that where are the exact values of it. So what values is like, okay, I want to see that where my mean of the data set is, where my mean plus minus first standard deviation lies along, where the second standard deviation is, where the third standard deviation is. Okay. So we see something like this. So how I did is there's a function called as AXV line. So that is nothing but plot the x-axis as a vertical line. So that is nothing but plot something on the axis, a vertical line, V line. Okay. So, and then you can just give certain colors, variables, style lines, and then line width that you want to do. Okay. Something is happening in the lobby. 2 minutes. Okay.
Ma'am,
So if you, hi, yes.
what does 0, 1, and 1000 represent in this?
Nothing.
Code?
So nothing. It's just that I'm taking some random values within 0 and 1, and those are like how many values? So those are like 1000 values. So this is like n number of values that I have within my entire range is like only 0 to 1. Within those 0 to 1, I have like 1000 values. So you can
Okay,
take
ma'am.
n number of values there. So it just normally defined to just show you how a normal distribution might look like within those variables. I can just change it to some another variable. Say if it's 10, we'll have a skewed distribution, and which is towards, and not a skewed but normal, but that is scaled to another set of values. So just to show you. Okay, so here. So then if you see the first line, for this it is 0. Now here where is how our where our mean lies for the data. Okay, and this line is also where the median as well as mode of our data lies, is like maximum. This is normal distributed data. So all mean, median and mode are same. Now if you want to see something like, okay, what is the value? So you might have learned this in a particular lecture. So what this values would be, so empirically we scale them as with respect to standard deviation. So how we observe the data set. So for a normally distributed data, if the values are within plus or minus 1, so my x-axis here represents my standard deviation. Okay, so I say that, okay, within plus minus standard deviation, how much percent of the data set is within this particular 2 green bars of plus minus 1. So we say that there are 68%. So these are like some empirical constants that people who did experiments previously, they came up with these numbers, and then now we know that, okay, n number of data set, how many values would be in between them. Okay, so we say, yes, someone wants to say something? Go on. Okay, so then here we see that, okay, within plus minus standard deviation, we have like 68% of our population or the observation of the data. Similarly, for plus minus 2, the value was like 95%, plus minus 3, the value is like 99.7. So we say that n number of percentage falls within this particular distribution for this particular values. But the only limitation for these numbers is that it's only for the bell-shaped curve. Now, data is skewed, something like this, what we saw here. So if you plot this particular data set in the same way, and you want to know that what are the values in between plus minus 1 standard deviation. So for similar, it's like data set which are like skewed, what we follow is the Chebyshev's theorem. Now what Chebyshev's theorem does, that it has a particular formula where it takes some k value, and that k value would be like 1 minus 1 by k square, where you assume that k is greater than 1. So here you see that it's not following for negatively skewed data set or left tail data set. So what we do there is take a symmetry of the data set, make it positive, make it absolute terms, only in terms of its x-axis, and then you plot the symmetry of the data set and then follow this variable. So it would be 1 minus 1 by k square. So from there you'll be able to know that, okay, how much of the data set will lie within first standard deviation, second standard deviation, and then third. Okay. So this is how you measure the skewness of the data set. Lastly is that you want to see, okay, what is kurtosis? Now for kurtosis also, we have a particular inbuilt function. We won't just go and then take the peak and then see, okay, what's the maximum value of the data set. Now kurtosis will indeed tell you the peakedness of the distribution. So it says that a distribution can be leptokurtic, a distribution can be mesokurtic, or it can be platokurtic. Now, what this all three differences or words were, like if your distribution is leptokurtic, that means it's very high and thin. So it's very less dispersed, and it's has a very higher value. If it's mesokurtic, it's something like this, like a normally distributed data set. If it's platokurtic, something like, okay, it has a very plain value, it's flat and it is spread out. Okay. Now coming back to kurtosis over here, so we have like an inbuilt function from SciPy library, that is from scipy.stats. You can import this kurtosis. Suppose you take some n number of random variables and you just plot that particular data set. So your value for kurtosis is also defined in a way that it will be negative if, so kurtosis would be negative if it's platykurtic, it would be positive if, if it would be 0 if it's mesokurtic, that is normally distributed, would be positive if it will be leptokurtic, that is nothing but if it is high and thin. Okay. So if you just plot it, you see, okay, this was our data set, it is high and thin, and you have some value next to it. Yes, someone wants to say something?
Hello, ma'am.
Yes.
Ma'am, can you tell me this graph how to know this is high, positive, negative, and also 0? It's three type you tell me na. So is how to identify? Yes.
So you just see at the shape of your distribution. If your distribution is very high and thin, you say it's leptokurtic. If it's normally shaped data set, it's mesokurtic. Or if it's flat and spread out, it's platy. But based on kurtosis, we say that, okay, if your kurtosis is negative value, it's platykurtic. If it's 0, it's mesokurtic. And if it's positive, it's leptokurtic. So only for a leptokurtic distribution, which is like something like a normal or which follows normal distribution, but it has a very maximum value and it's not that dispersed. It has a very less dispersion. So that is where you have positive values. Okay. Someone else? Okay. People who have their hands raised, do you have anything? Okay, so if not, then yes, Sarvesh, you have something?
So, ma'am, am I audible first of all?
Yes, you are audible.
Yeah, so how do we quantify this peakedness of the graph, the data?
So you quantify it using kurtosis only. So you see of your data is this 3 values, and within where you just find the kurtosis of your data set and you give it. So following the particular value that you get, and within this 3 particular categories, you define the peakedness of your data set.
Okay, so this kurtosis, is it also used for skew? Okay, those are different, right? Kurtosis and skewness are different. Okay, thank you, ma'am.
Yeah, yes. Thank you. Okay, someone else? I see 2 people have their hands raised. You have something? Yes. You're not audible. Whoever's trying to say something, he or she is not audible. Your voice is cracking. Okay. So now this was all about how it was and how different plots and tendencies are. Yes. Okay. Please, if you have something to say, then only turn on your mics on. If not, then we'll go. It's like if you have something to say, raise your hands first. I can call out your names and then later you can turn your mic on. Yes, Tharun? Okay. So now the next week was all about probability. Now probability, it's like whenever we hear of the term probability, it's all like we come cards, dice, wheels, everything comes to our mind because we have always seen, okay, if their spade comes, a diamond comes, a heart comes, or how many times I roll a die, what will come. So these are all like a different variations where how we see a particular data set, or it's like how we see events are likely to occur. So now why we want to see this or we want to compare this is that we want to comprehend different ways how to estimate a data set. We want to assign different specific values to it. We want to see how different likely events occur. So probability, what probability is that it's a branch of mathematics that will calculate, estimate, or will simulate, will give you the likelihood of a particular given element or event that is going to happen. Okay. Now, you all might have this similar things as like if you have done you're in your bachelor's, your competitive exams for going through this might also have had this simple probability and statistical based methods. Now, to be honest, I don't like probability. I was always a stats kind of person, and in my own PhD interview, I was asked about probability and I failed to answer it, and I was like, oh, so much feeling guilt or depressed. Okay, I was not able to solve it. I was like, okay. Because of that, we need to understand that how to solve using different laws of probability, need to understand the situation, if it's an additional probability, a multiplicative, or if it's a conditional probability. And then we'll see different rules for the same also. So here I've not included all the rules because in the slides everything was. So just a quick poll from everyone that what you all think, can probability be negative or probability has a range of values to be a certain to?
0 to 1.
Yes, certain ranges.
Yeah, yes.
Yes, and
So
0
it
to 1 probability or not all negative.
Yeah, yes. So probability of a particular event, or say probability of A, is always restricted from 0 to 1, and it's not negative. So we say that there are different kind of events. We have mutually exclusive events, we have independent events. Some events which their own probability won't be affected to another events, whereas some events who are likely to affect another events and hence they are not. So there are this kind of variables. Now, the range of probabilities where we say it's 0, so that's like an impossible event to happen. It's 50%, so you have a likely chance, and it's 1, so we say a certain chance. There are different methods to estimate probability. Okay. There's classical methods, there are relative methods, and then you have subjective methods. Okay, then you have subjective methods. So you have methods are more based on your personal intuition or reasoning that you follow, whereas relative methods are like you see how cumulated the data is. Okay, see how cumulated your data is followed on the previous frequencies of occurrence of them. Okay, similar to classical method, where you just see that how the data set follows certain rules and laws. Okay, so for classical probability as well as for subjective probability, both are defined. Whereas for classical as well as the relative terms, yes, Tarun, you want to say something? Okay, so now for probability, there are different terminologies. What we have is like we have a particular experiment. What that experiment is, that will produce an outcome. Now, within an outcome, we say there is for a particular outcome, we follow a single trial. Per trial, we get an outcome. Now, what's a trial? Trial is a repetition of processes that comes through. Following a trial, you have an elementary trial or elementary experiment. That is nothing but a very preliminary thing which cannot be broken down to certain normal pieces. It is actually a very first part to begin with. And then lastly, you have an event to accumulate all of the above. That is like you have an outcome of an experiment that can be an elementary experiment or can be aggregate of all of them. Okay. So then we have something called a sample space. What a sample space is? Sample space is something that you have. Yes. Okay. So for a sample space, it's like, okay, how many particular variables that you have within to choose your probability of an event to. Okay, so mutually exclusive events in it follows that. Yes, Rohit? Okay, we'll just go forward. So in a way, we have mutually exclusive events which are not together, independent events who does not have an effect of first event on the second event. There are also events called as collectively exhaustive events. What those events are like, where you say, okay, if you roll a die, you'll get almost like 1, 2, 3, 4, 5, 6. So there, all the outcomes that you get is like 1, 2, 3, 4, 5, 6 are mutually exclusive of each other. Now, can someone say what are complementary events? So
If
if I
any
have
event happened, then another event is not happened. It is
yeah, yes. So if I want to
like
find
complement.
the
Matlab, if
probability
happened,
of
then it is
that,
not happened.
yes,
I
yes, yes.
think 1, then it is minus is not happen if
Yeah, actually. So if I want to compute the probability of that complementary event which didn't exist, we'll compute something that, okay, probability of getting a 2 on the dice is something that is favorable event to me. And what would be a complementary event that I don't want to get a 2 die? It's like, so probability of getting a 2 in the die would be like 1 by 6, and not getting 2 would be like 5 by 6. So how I get 5 by 6 is like 1 minus 1 by 6 is 5 by 6. Okay. Then okay. Okay. Then what we do is like we find certain combinations of events. So there are okay. So let's just have certain compute certain possibilities. So okay, I have 2 coins and I coin 2 of them, and I have n number of events, simple events. So I want to count the possibilities of them. So how many possibilities would be there? Is like possibilities of event 1 times possibilities of event 2, or possibilities of coin 1 times possibilities of coin 2. So coin can only have 2 sides of it. So that's like 2 times 2 is 4. Where say something that you're choosing with replacement and without replacement. So there are also rules which are like, okay, we say that I have a bag of balls, and within that bag of balls, I'm drawing some balls that are like with replacement, without replacement. In that cases, if it's with replacement, we say that, okay, the n number of events would remain the same. So if I have say something like 1,000 balls to take, and then I have like 3 random events where I can plug those 1,000 balls. So it would be 1,000 times 1,000 times 1,000. So it's like 1,000 raised to 3 n number of trials or counting possibilities are possible there. Okay. Now in some situations where this particular thing is not possible, what we apply is combinations. That is nothing but NCN, where I guess everyone here knows that that is nothing but nth factorial divided by nth factorial, where it's x minus n. So there x stands for your total possibilities and n is your event number of possibilities. Okay. Then for this particular things, you have rules. So here, if you see how people also distribute or show this probability graphs is like based on this tree diagrams. So if you have certain number of variables, say A, B, C, D, and then you can also have combinations of them. So A with B, C, D, B with A, C, D, C with A, B, D, and then D with A, B, C. So you have this likely number of events. Again, with each of them, you also have n number of events. So seeing how many variables you have, you can plot those tree diagrams, and accordingly it would be easy for you to compute a probability of it. Then you do Venn diagrams. Venn diagrams, like you plot each and every variable, you see how it is falling. Now, if say I have 2 events, say x and n a particular event, and I want to see a union of them, is like the probability of having x and n together. I do union of them. If I want to see, so this particular case, what is shown over here is for intersection. So if I want to see what's the intersection of them, so I see only the region that's highlighted in blue. If I want to see something that is only for x, so probability of x which does not have y, so that is like complementary of y. So that would be only with this particular region and not the intersection region. So for that, what we'll do is like we have x value, we have the intersection value, we subtract the intersection from the x value. Okay. Similarly, for only y, we do this. If you want to know for the entire green area out there and not within the circle, so you know the probability of union of p, x and y. So that is nothing but p of x plus p of y minus p of x intersection y. So the in-between region of them. So that way, if you have that, and this is just the complementary of the outside one, so you just do 1 minus p of x union y. So that is how you compute this all thing. So these are like pretty much basic laws, and then there are different kind of numericals that are solved in the lecture that you'll be able to understand if you don't just get for now. So there's like different terms that you should be now thorough with for if you're learning probability. There's marginal probability if there's only a single event, an event of x is like probability of an event x occurring. So that is only for x. Union, when we take for both of them. Joint probability is like probability of both of them occurring together. That is how we also call it as an intersection. And then there's conditioned probability, that which says that, okay, what if my event x is occurring given that y has already occurred? So that definition is like it will follow Bayes' rule. So that is something that probability of x intersection y by probability of y. So you have different rules and theorems, and you have the derivation of the same in the lecture slides also. So I won't repeat the same theory here. That is why I have skipped those points here. So now I guess we come to the end of this session, live session. If anyone has any doubts, they can ask, or else we can go to the assignment hour so that it will help you to assign us, like solve the assignment that is due tomorrow. Any questions?
Ma'am, you can give me just a quick summary.
Or
A quick summary.
about the entire thing?
No, just whatever happened in the last half an hour.
Oh, okay. So last half an hour, we just started with what is there in the week 2 of probability. In the class, sir has given different rules. He has stated different numericals there also. So here I've just highlighted few things that would be helpful for you to solve the assignment questions, as like what all things are necessary to keep in mind. Then we also saw using Python codes that how you should plot your data, how to know a particular data is skewed or not. We saw what are the dispersion statistics of them, and we saw how to is like plot those particular statistics, how to see the values of them, the significance of the statistics, how we compute the values of it. So these are all the values that we saw today. We also saw how to plot a scatter plot, how to differentiate data in between two different groups if you want to. So these was all like a handful of theory, handful of practical session. Okay, if no
Thank you.
further doubts. Okay, thank you. We can continue with the assignment thing. Okay. So I want quick answers from everyone here so that you all can also be free. I can also be free, and you'll be able to solve the assignment that is due tomorrow. So first question, which of the following is each individual outcome of an experiment called? You can unmute yourself at your will and say the answer out loud. So an individual outcome of an experiment is called what?
Sample point.
It's a sample point. Yes, it's a sample point. Next, a process that generates well-defined outcomes is called as?
An experiment.
Yes, so an experiment is something that will give you an outcome value, and a trial or an event is something that's a repetition of a one particular experimental value. Okay. Then two events having a non-zero probability can be what? So can they be mutually exclusive or not, or can they be independent? So they have, both of them have non-zero probabilities. Now I'm not saying over here that one event has a non-zero probability or one event is dependent on each other or not. So nothing like that is given to us. So can we say about them?
Can't be both mutually exclusive.
And yes, so if nothing is given to us and no such information is given to us, so we can't say that both can be mutually exclusive and independent. Okay. Next, a normal distribution with a standard deviation of 1 that we just saw and mean of 0 is defined as? Well, the answer here is given. Yeah, yes, Nikita?
Standard normal distribution.
Yeah, yes. So here the options are just to confuse you that it's an ordinary normal curve or it's a probability density function, because it's the plot that we define as a probability density function, and then we fit a particular distribution with a probability density function on. So it's just a normal distribution, and that is where the question also has an answer in it. Okay, in a standard normal probability distribution, the area to the left portion of the mean is equal to. So now left portion of the mean suggests something that your data set is what? With skewed?
Negatively skewed.
Yeah, so if it's negatively skewed, can we say that the area is negative?
Yes.
No, we can't say, right? Because probability only exists between 0 to 1. Area is always positive. So what the left portion of the mean? So here area is just an absolute quantity that we are talking about. So what it would be?
0.5.
0.5.
Yes, 0.5. So it would be 0.5. Next question is something that you all might have, I don't know if sir had solved a similar question or not. I actually didn't get time to visit the last lecture. So it's something based on z-score. So the weight of football players is normally distributed with a mean of 200 pounds and a standard deviation of 25. The probability of a player weighing more than this. So for that, you'll need a Z table. But if it's fine if you can just tell me the Z value and we'll proceed with it. So how do you proceed here to solve it? So you have mean, you have standard deviation. What's the value to compute the Z score? The formula of it?
Subtraction between the means divided by standard deviation.
Yes, so subtraction of what? A sample minus mean divided by standard deviation. So what we do over here is we want to find the probability of that particular player, say player X, that is greater than 241.25. So what we do is like we do X, so 241.25 minus 200 divided by standard deviation, that is 25. Everyone clear on this point? I suppose yes. So for that we get something as 1.65, and if we take we see the Z-score table and we plot it and see, so we just see is like we just hover over to the table, we'll be able to see where the probability lies along. So for here the value was like this. I hope you all know how to read a Z table. Yeah, yes.
0.0495.
Yeah, yes, exactly. If anyone does not know how to read a Z table, you can let me know towards the end of the session. We'll see that. Okay. Okay. Next question. Similar. So the probability of a player, say if it's less than that. So what do we do there? We just take 1 minus of it, or we just go again the table. Oh no, the value has changed now. So it's 250 pounds and that's lesser than that. So we'll have to look at the backside of the Z table now and do the similar calculation of the Z scores, like X minus mu by sigma. Okay. So the answer for this one is 0.9772. Okay. Next is the Poisson's distribution is which of the following type? Is it a probability distribution, or it's a discrete, uniform, or normal?
0.977.
Continuous.
Poisson's distribution is continuous?
Continuous probability distribution.
Discrete probability distribution is right answer.
Which one?
Discrete.
Okay. Why discrete?
Because
Because someone was saying something. Well, because over here.
Discrete probability distribution.
Yes, but why discrete?
The values are discrete. It doesn't like it is not related.
Yeah, yes. So they occur within a given frame of time. So the values are it's like the events are likely to occur the time frame of time that we have, and it's not continuously stable, similar to normal distribution. So that is why Poisson's distribution, discrete probability distribution. Okay. Now assume a binomial experiment with p is 0.5 and a sample size of 100, what the expected value of this distribution would be. Well, I guess we didn't see this point, but expectation, variance of expectation, there are simple formulas for it. So to find an expectation of something, it is nothing but we multiply the sample size with the probability of it. So for this, what we'll do is like we'll multiply what? So the formula is NP. So what the answer would be?
50.
50.
The formula is NP. I actually didn't hear some of you. So the answer would be like 0.5 times 100. Yes, 50. So it's like this D option. Okay. Last question. So if it's a hypergeometric probability distribution function, what it is identical to? So Poisson's distribution, we saw that, okay, it was a discrete, it's not hypergeometric. Now what hypergeometric here in this sense tells us that it also has a sense of exponential distribution, logarithmic distribution, and the values are not converging anywhere. So does binomial, normal, or Poisson has those things?
binomial does have?
Binomial has.
I think the value in binomial probability lies between two sets.
So, okay.
I think both.
So, okay. So, of how it works is like for a binomial distribution, the probability is like same for each and every trial. But if it's a hypergeometric distribution, each and every trial will change the probability of your distribution, and subsequently over subsequent trials, considering there's no repeat of those trials. So that is how binomial and hypergeometric distributions are also different. So that is how I feel for now, and I'll also recheck this again if you say, guys. So for now, the answer is like none of these, but I'll cross check for based on my understanding. I feel that both of them are different, and hence it's not an alternative here for hypergeometric distribution. Okay, with this, we end with today's session. And if someone wants to know how to see, read Z tables, you can stay back and I can show you. Okay. Someone has something? Yes, Tarun. Yes, Govindu. Like if you're done, if you don't have any questions, you are free to leave the meeting. We are done. We also have an it's like simultaneous session going on with another TA that is from 7 to 9. So if you want to join there, you can also join there. Similar content would be there, but might be some another useful information that you need to know. So if you want, you can just go hover around and have a look at that session as well.
Ma'am, before this session, how many sessions has happened?
So it only started yesterday and the other TS started from last Tuesday. So this is the second session for both of us.
Okay, I'm joining for the first time. And this session happens regularly or weekly?
Weekly, every Tuesday from 6 to 8 for mine, and for the other TA it's like 7 to 9.
So the course covered in the session will be same, like.
Yeah, so we are supposed to give you a summary about the entire lecture that was there uploaded online if you don't get enough time, and then to help you solve the assignment questions that are due next day of our session.
All right, thank you.
Thank you. Someone else wants to say something? Govindu, Tharun, and Rupansha.
Good evening, ma'am.
Yes, Rupansha.
Ma'am, can you explain that Z table?
Oh, yes, I can show you the Z table.
Before that, ma'am, good evening.
Yeah, yes.
We are from NPTCL course, NPTEL. Would we get the links of every session like we got it now? To our emails and all.
For every what? I didn't understand.
For every session, will be getting the links that the way we got now.
Yes, yes. So links are uploaded on the platform only, on the NPTEL platform, your course platform. So if you see on announcements, the links would be there to join the particular session. Also, before the session, a quick reminder kind of thing would also be posted.
Thank you.
Thank you. Yeah, so someone who just said here.
Table ma'am.
Sorry. Okay, so if you see over here, there's an example as, okay, you have average of 200 hours, so that's your average. This is your standard deviation. And then you have how many expected days or more than this, you'll be there. So this is the probability that you have to find along. So this is your x, this is your mean, this is your standard deviation. You find the z value. Now for z is 1.33, how you find is you will have these values of 1.3, go till 0.03, you find the probability. Now, how do you see that? Okay, if it's only for greater than or less than, so across your distribution, you'll have the values as now. This values is something for the table that is less than the value. So P, probability of Z that is less than 1.33, the value of probability is something like this. Now, if you want to find for the another extreme, so you'll do something as 1 minus this. So what you got is for the less than value. Now you take out the value for this and then you do a percentage of it, like multiplied by 100, you get that. Okay. Similarly, if you want to find out for the other extreme, so whatever value that you find would be the answer of the extreme. So it's like value that is less than that particular variable. So if you see over here, I guess similar example is there, but only your x differed over here, and the value that you got was negative 1.677. Okay, so for negative value, if you flip the table back, there are in stationery, if you go or even online, you will be able to get this z tables. If you flip the table, there are negative probability values. So if you see a negative z scores. So if you see it for negative 1.6, you also hover it around for 0.07. That is, we want to find for 1.667. You find the probability and then you get the probability of 0.0475. Now, if I wanted to find over here that probability of something that is like probability of x where it is less than 75. And this table indeed gave me probability when it is lesser than that. So hence I get this particular distribution value is less. So that is even that only I won't be subtracting it because I don't want a complementary value of it. Okay. Similarly, here, if I want to find the probability of x something that is less than 175, I do a similar thing. I got the probability. Okay, I hope now it is clear. Have any queries now? For how to read a z table and how to find the values of probability? Thank you. Thank you.
Ma'am, in short, can you explain what is bins?
Oh, yes. So bins are something that you give as, okay. So let's just say I have some n number of variables, or say I have n number of things in my room and I want to organize it. So I'll say my one bin, my one particular box will have a particular number of things in my that are there in my room. So I'll say, okay, all the electronics things would be in one box, another would be in one box. So what we do over here is we bin the data set. So we define a width of a bin in a way that we want n number of values of frequencies to lie within it. So it would be just added in it. So my data is then categorized. So if I gave say n equals to 50 number of bins that I want or 100 number of bins. So I'll have my data set arranged in a way that it has 100 such bins or buckets, and it will in each particular bucket values of similar frequency, how many times they occurred in a data set would be aligned or will be thrown in. So that is how we plot a histogram or a particular bar chart or bar graphs like that.
Thank you, ma'am.
Thank you. You're trying to say something, but your voice is cracking. Sorry, your voice is cracking. Okay, Govind, do you have something to say?
No, madam.
Okay, thank you. It's like I saw
Thank
your
you,
hand
ma'am.
was raised. That's why I asked you. Okay. Tharun, Azmira, you have something to say? Okay, if not, in next 10 minutes, we'll end the session. Those who have any doubts, you can just tell me. I'll be mute till then, and you can let me know. Okay, yes, Bindu Ishwara. Okay. Okay, if no one has anything to say or you have no doubts, then I'll end the session for today. We'll meet next Tuesday to see for coming week's week 3 session. And now I guess if you have some time, you can go and join another TS session. He'll also have the similar content and probably some more insights into it or something related to Python. And you can learn a bit more if you want to. Okay, with that, I end today's session. Thank you. Bye bye. Good night.